Hi everybody. We're going to get a little practice finding areas of some regular polygons. Look at this first one. What an interesting thing. It's inscribed in a circle. Consider a regular nonagon inscribed in circle X. And we might remember that a nonagon has 9 sides. I'm going to write 9 sides. I'm going to write that n is equal to 9. I think that's going to be important to me. Each of the sides are 10 millimeters. So I guess the perimeter, I think, will be 90, huh? That might be important to me later when I'm finding areas of things. But give the measure of the central angle. Now this is a very important concept. Any central angle, that would be like, we want to think of the smallest one. Cutting just a single arc of just a single side. How big would that have to have been? And because this circle has been divided into 9 equal parts, 360 divided by 9 forces this to be a 40-degree angle, 40 degrees of arc right there. So that central angle would also have been 40 degrees, because we know a central angle is the same as the arc it cuts. So the measure of angle AXB got to be 40 degrees. Show the trigonometry used to find the length of the apothem of the polygon and the radius of the circle. Now that's an interesting thing. We know the length of this side, and we know the measure of this angle. That's 40 degrees of arc. But the length of that side, that's 10, isn't it? Let me draw that triangle again. I think you probably should too. Just talking about triangle AXB. And we're going to put that arc there as well. That was 40 degrees of arc, give me a 40-degree angle there, and this length was 10. But let me show an apothem, reminding you that the apothem is the distance from the center of a polygon to a side of the polygon. And it's going to go to that midpoint every time. I'm going to do the same thing here. So I think that length has to be 5. And this one would have been 5. I know that apothem is going to bisect that side of the polygon. And now, this angle would have been 20. We figured out that central angle was 40, so this angle would have been 20. And here's the right triangle I'm going to work with. I can just do some right triangle trigonometry. And I'm going to find the length of the apothem. I think I can work that probably right here. I want to know, if I use that 20-degree angle, I want to know the length of the adjacent side, and I know the length of the opposite side. And opposite and adjacent make me think of tangent. You might want to write SOHCAHTOA there to get that thought going. Since tangent is opposite over adjacent, and I wish I knew the adjacent, but I do know the opposite, I'm going to say that the tangent of 20 is equal to 5 over the apothem, because the apothem is the adjacent side. And I'm going to figure out what is the tangent of 20. Got my calculator handy. Turn it on. Check the mode. I'm degree mode. I'm happy to report. And I want the tangent of 20 degrees. And that's going to tell me about 0.3640 if I were to round that to the nearest 10,000th. 0.3640. 3640 over 1. And you look at this proportion. 5 over AP, that's equal to the tangent of 20. Tangent of 20 was equal to opposite over adjacent. And the tangent of 20 is equal to 0.364 over 1. So what would I do to solve this proportion? I know I'm going to cross multiply and divide, but that's going to entail that I'm just going to be 1 times 5 is equal to 0.3640 times AP. So I think it's going to be 5 divided by 0.3640. 5 divided by 0.3640. Yep. I'll think that right. So I come up with 13.736. I'm going to call. What am I going to round this to? Does it tell me to round to the nearest hundredth? Okay. So 13.74. The apothem is 13.74. But it also asks me for the radius of the circle. And the radius of the circle, that piece like AX right there would be the radius of the circle. It's also this length right there. This is not a 3069 or anything like that. I can't just double the short side to get that hypotenuse. But I do have I do know this angle is 20. I wish I knew the hypotenuse. I do know the opposite side. I could use sine. Sine is opposite over hypotenuse, and the sine of 20 would be 5 over, I'm going to call this R, because it is the radius of the polygon. So the sine of 20 is equal to 5 over r. What else is the sine of 20 equal to? We'll figure that out pretty quick. The sine of 20 is 0.3420. 0.3420. I should equate those two things. This is equal to the sine of 20 and that's equal to the sine of 20, so I come up with 5 over r is equal to 0.3423, excuse me, 0.3420 over 1. And what do I do to solve that proportion? I'm going to divide, aren't I? It's 5 divided by 0.3420. We'll do that right away. 5 divided by 0.3420, giving me 14 point, I'm going to round this to the nearest hundredth, 14.62. That's the radius, huh? 14.62. Okay, it's done a little trigonometry, and now we know the radius of this polygon and the apothem of the polygon. Give the area of the nonagon and the area of the circle. I'm going to round those to the nearest hundredth. Area of the regular polygon is going to be 1/2 times its perimeter times its apothem. So we're just going to lay in the things that we know. And the perimeter of this thing has 9 sides, and they're all 10. So the perimeter would have been 90. And we just did find the apothem to be 13.74, huh? About 13.74. So I can use that formula, 1/2 times the perimeter times the apothem, to get it pretty cleanly done. Let's see if we can agree on this. 0.5 times the perimeter of 90 times the apothem of 13.74. That looks all correctly entered. So I come up with 618.3. Unit squared. That's the area of our polygon, which is very close to the area of that circle. Wouldn't you say that circle's just about the same size? A little bit bigger. It better be a little bit bigger. Let's find the area of the circle. And I know that the area of a circle is given by pi times the radius squared. That's a formula you're going to want to keep handy with you for the next couple of 3 weeks, huh? Area of this circle is going to be pi times, and we found the radius to be 14.62. 14.62 squared. And while I like to leave things in terms of pi, here I'm going to go ahead and round it to the nearest, I'm going to substitute for pi and round to the nearest 100th. So you do those calculations, let's compare our answers. Pi times 14.62, 62 squared. I'm coming up with 671.497, 671.50. 671.50 units squared. That's for the area of the circle. Now, here's a pretty good question. Give the area of the shaded zone. And this is the shaded zone inside that circle but outside that polygon. How in blazes could we possibly find that? Inside the circle, outside the polygon? Yeah, it would be I think to myself, it's the area of the circle minus the area of the polygon. That ought to give you the area that is shaded. That's a nice thing to remember. So, the area this time, let me just show that process best I could. It would be 671.50 minus the area of the polygon, which was 618, pretty close, 0.3. Still got the area of the polygon on my computer, my calculator. I'm just going to subtract from that 618.3. And I think we should agree that it's about 53.197, so about 53.20. If I round that to the nearest hundredth. 53.20 units squared. That would be the area inside the circle, but outside the polygon, all this little shaded stuff. Give the area of one segment of this circle. And you're saying to yourself, well, what the heck is a segment of a circle? And I would tell you, this is a segment of a circle. One of those little areas right there, bounded by a chord and an arc. And these various segments are all the same size, and they add up to this amount, don't they? That is the area of all those segments put together. And we got 9 of them. So if I wanted to get the area of a single segment, it would have to be that, the total area, 53.20 divided by 9. And I'll get the area of that little zone right there. Already got the 53.20 pretty much on my calculator. I'm just going to divide that by 9. I'll get it pretty close to the right answer. About 5.91. 5.91 units squared. That's the area of each one of those segments. You're going to hear more about segments from me coming up in the next assignment. But let's look at these right now. A regular octagon. And the radius is 12. So they give me different aspects. Last time they gave me the size, this time they give me the radius. Use some trigonometry to find the length of the apothem and the length of the side of the polygon. Okay, so we got to think about this triangle. So what about that central angle in this octagon? We're going to have to know about it, don't we? What we should know about that central angle is it's going to be 360 divided by 8. And that makes that central angle be 45 degrees right there. This one would have been 45 degrees. Use some trigonometry to find the length of the apothem and the length of the side. Let me show an apothem. That just is from the center of the polygon to a side. And then we're going to find that little length right there from B to that midpoint where the apothem hits. And we'll have to double that to get the length of each side of the polygon. Then we could probably get the perimeter and get the area. Let me work with that right triangle that I just did draw. I know the hypotenuse is 12 because the radius was 12. And that this full angle was 45, so this small angle that we got right there is just a half of 45, be 22.5 degrees. 22.5 degrees, I'll call it, I guess. And I would like to get the length of the apothem first. I'll call it A. Working on that right triangle, I think I'll be able to get the length of the apothem. Thinking about SOHCAHTOA, and you think that through too, but I wish I knew the adjacent, and I do know the hypotenuse, and adjacent hypotenuse make me think of cosine. So cosine of 22.5 has to equal adjacent, that's A, over hypotenuse, that's 12. Let me just go forward in that and come up with a cosine of 22.5. And that turns out to be 0.9239. 9239 over 1. You study that proportion with me, and you decide what we got to do to get A out of it, the apothem out of it. Yeah, I'm just going to multiply 12 times 0.9239, huh? So 12 times what I had in my calculator before, second answer, and I'm coming up with 11.086. So I had to call that 11.09. The apothem of 11.09 units squared. Nope, that's not square units, that's just units. Excuse me, that's just the apothem. Now what about the length of the side of the polygon? We want to get the apothem when we've done it. Now we want to get the side. I'm going to get this length right there that I'm calling X, and that's really that little length there. We'll have to double it to get the length of the side. But if you wanted X in that polygon, wouldn't you use some trigonometry? I guess you could use the Pythagorean theorem now that you know the apothem, but I'm going to use the trigonometry. I wish I knew the opposite, and I do know the hypotenuse. That makes me think sine. Sine of 22.5 is equal to opposite, that's X, over hypotenuse, that's 12. Let's see if I can go further with that equation and come up with a sine of 22.5. And I come up with 0.3827. 0.3827 over 1. There's a proportion to be solved right there, huh? But we ought to be able to get X out of that. And what would you have to do? Just 1 times X is going to equal that product, so just 0.3827 times 12. I'm going to go with the number on my calculator, times 12. And I'll say about 4.59. 4.59 is this length X right there. But wouldn't we double it to get the length of the side? That's what we'll have to do. I'm going to say BC, which is the length of the side, is twice this amount, twice 4.59. So I have about 9.18. That's how big each side is on this guy. Show the process as you find the area of the polygon. 1/2 times the perimeter times the apothem. Yeah, we're ready for that. 1/2 times, hey, what was the perimeter? It seemed like we knew something about that. So the radius was 12, and we built this thing, so we know that BC was 9.18. We got 8 sides that big. I'm going to say times 8. And I got the perimeter, 73.44, huh? Times the apothem, which we found to be 11.09. Put some parentheses around this for good form. 11.09. And I'm just going to go left to right with my calculator and come up with that amount. 0.5 times 73.44 times 11.09. And I have 407.22. That's unit squared, isn't it? That's the area. Now, this is kind of an interesting thing. Use the fact that the central angle is 45 to find the area of the one of those smaller triangles. I think I can do that. If this angle is 45, thinking this triangle BCX, that's what I was thinking earlier. I wanted to do this. And that's a 45-degree angle. If I were to just make and we do know how long the radius is, don't we? The radius on this thing we found is to be 12, so that length would be 12. And if I dropped an altitude right there, this is a 45, 45, 90, isn't it? Just an alternate way to get this thing done. If the hypotenuse is 12, how long would that have to be? Well, I really want the altitude, don't I? Both of those sides are going to be 12 divided by the square root of 2, so 6 square roots of 2. I'm going to come up with the area of that triangle right now. 1/2 times this base. And this is 12. This is also 12. Yeah, this is 12, and I just dropped an altitude right there. So it's 1/2 times 12 times that altitude of 6 square roots of 2. 1/2 of 12 is going to give me 6 times 6 square roots of 2, and 6 times 6 square roots of 2 is 36 square roots of 2. That's what I think is the area of that triangle right there. But how many triangles like that you got? I think in this octagon I got to have 8. So I'm going to multiply that times 8. See if I can't get that pretty quickly done. 36 square roots of 2. Let me clear that. Let me just do 36 times 8. And I come up with 288 square roots of 2. Calculate the area of the polygon this time. And I come up with 288, that's 36 times 8 square roots of 2. Now that's what I think the polygon is this time, but last time we thought the polygon was this much. Let's see how those consider, how close they are to each other. We come in with 288 square roots of 2. It tells me that should be 407.29, and that's pretty close to what we got last time, isn't it? It may be off by a little bit, by some hundredths, but not bad at all. Yeah, this is the true area, 288 square roots of 2. We rounded some stuff over there. Give the area of the shaded zone inside the circle, but outside the polygon. Now, how am I going to get the area inside the circle, but outside the polygon? This shaded stuff. That'll be the area of the circle minus the area of the polygon. That'll be the area of the shade. Now, let's get the area of that circle. Do we know its radius? And yes, we do. The radius was 12. So the area of the circle is going to be 144 pi minus. Did you get the area of that polygon, mister? Yeah, as a matter of fact, it was 288 square roots of 2, huh? That was a better answer. So that's really the area right there. We could get a decimal on it. That'd be okay. I guess I will get a decimal for it, but I'm liking the way that answer looks. 144 pi minus 288 square roots of 2. Makes you want to do things with it because both, well, never mind. Let's just get a decimal number on that. 144 pi minus 288 square roots of 2. That'd be about 45.1, 45.095. Can I call that 45.10, huh? Yep. 45.10 units squared. That would be the area inside the circle, but outside the polygon. Give the area of one segment of that circle. Now, if all these segments, all these little areas right here add up to 45.10, how big would each one of them be? because they're all the same size, there'd be 8 of them, and it's going to be that 45.10 divided by 8. Not too big an area. Let's take a look at it. I'll just take that number divided by 8. So it's about 5.34. 5.34 equals the area of a segment. So that's a nice thing to work with. And you got something like this to work with too. I think it looks like this guy. Area workout 2 with regular polygons. So you do that as the next assignment, and we'll be talking about that one too. Appreciate all your work. Thank you very much.